Hey guys, so we are on the last lesson for logarithms and exponential functions. Today we are going to be talking about growth and decay modeling. Usually when you look at exponential functions, the general equation or the general form for most exponential functions will look like this. So we have y equals ab to the power of x. Okay, so where a is our initial amount, b is our growth or decay factor, and x is the amount of time that has passed, and it's usually in years. Right, so looking at the function, we need to be able to know whether or not it's a growth function or a decay function. So with growth, that would be when a is a positive number, so it's greater than 0, and b is greater than 1. Okay, so if a is a positive number and b is greater than 1, then our b would be a growth factor. Alright, and decay. Our a is also a positive number. However, our b is going to be in between 0 and 1. So it's usually a decimal less than 1, and it's a positive number. Okay? So when we're dealing with growth and decay problems, usually we're dealing with word problems. So bear with me while I write all the word problems that we're going to be talking about today. Let's look at our first example. Okay, so our example reads, the population of a town in 2003 was estimated to be 35,000 people with an annual growth rate of 2.4%. Right, so part A of this problem is that we need to figure out what our growth factor is. Okay, so we have a growth rate of 2.4%. Okay, your growth factor is always that percentage plus 1. So it's always 1 plus the percentage. So in this case, we need to change the percentage to decimal form, and if you don't remember how to do that, it's your decimal your percentage, 2.4 divided by 100, which would give us 0.024. Or if you remember, you can move the decimal to the left 2 times. Okay, so our growth factor would be 1 plus 0.024, which gives us 1.024. Alright. Part B of this problem is that we're going to write an equation to model the growth. Okay, so remember, using y equals ab to the power of x, we are going to create an equation for this problem specifically. And this is what modeling is in mathematics. So we have A. In this example, our initial amount was 35,000. Our B is what we figured out in part A. Our B is our growth factor, so 1.024. And X still represents the amount of time. Okay, so we are creating an equation with respect to time, or respect to X. So our equation is going to be y equals 35,000 times 1.024 to the power of x. Alright, so part C of this problem, we're going to figure out how much the population would be in 2007. What would the estimate, or the estimated population be in 2007? What was it? So we'll use our equation that we found in part B, y equals 35,000 times 1.024 to the power of x. Okay, but how much time has passed between 2003 and 2007? So 4 years, so our x now becomes 4. Alright, we can type that in our calculator just how I have it written. And we get approximately 38,500. I just rounded that to the nearest hundred. Be careful when you're doing growth and decay problems, or any word problem really. Be careful with your rounding. If you get like some crazy decimal number, you can't leave that as your answer, right? You can't have half of a person. So your population isn't going to be 3 million point 6. You can't have 0.6 of a person. Right, so make sure you round it by just dropping your decimal. So it's not really rounding, you're just getting rid of the decimal. Okay, let's look at another example. Okay, so this example says Marissa invests $300 at a bank that offers 5% interest compounded annually. Right, so part A this time, again, we're looking for our growth factor. Remember, it's 1 plus our percentage. Okay, our percentage in decimal form is 0.05. So 1 plus 0.05, our growth factor is 1.05. Right, part B is to write an equation. So again, using y equals a e to the power of x. Alright, what is our A? Our initial amount, 300. Our growth factor is what we just found, 1.05. And then x would be the amount of time in years. Okay, so for this problem, our C is a little different from our last problem. This time, I want to know how many years I want to know how many years it will take the money to double. Okay, so this time I'm not looking for the end amount after a certain amount of years. I know what the end amount is. If my initial amount is 300, to double it would be 600. So we have our equation from B, y equals 300 times 1.05 to the power of x. Okay, I know what y is. Y would be my ending amount, or double. So 600, because 300 times 2, or double of 300 is 600, equals 300.05. And x is still x. Okay, that's what we're looking for this time. We're looking for the amount of years it will take for the money to double. Okay, so now we're going to just solve this. The first thing we need to do is divide both sides by 300. 600 divided by 300 is 2. Okay, and now we have an exponential equation. And the best thing to do when we have an exponential equation is to take the logarithm of both sides. Okay, and then we can use our power property to bring this x out front. Right, and then we'll divide both sides. Divide both sides by log 1.05. And then we can type this in our calculator. Make sure that you are using your parentheses correctly. x is about 14.2, so it's about 14.2 years it would take for Marissa's money to double. Alright, let's look at a decay problem. Oh, sorry. Okay, so it says Matt bought a car at a cost of $25,000. The car depreciates approximately 15% each year. Alright, so this time instead of finding a growth factor, we are finding the decay factor. Okay, and words like decay, in this case depreciate, decrease, okay, those are what let you know that you're finding the decay factor, not the growth factor. Alright, so this time it says 15% each year. Okay, when you're finding the decay factor, instead of doing 1 plus the percentage, it's 1 minus the percentage. And in this case, my percentage would be 0.15, so 1 minus 0.15. My decay factor is going to be 0.85. Right, my equation. Y equals my initial amount, 25,000. My decay factor, 0.85 to the power of x. Okay, part C. How much will the car cost in 10 years? Okay, so in this case we just plug in 10 for our x. And we get approximately 4,921.86. And remember, when you have money, to round to 2 decimal places, because these are your cents. Alright, so that's the general growth and growth and decay formula. Now we're going to look at compounding interest. So the next two formulas are when the interest is either compounded continuously or if it's compounded more than once a year. So let's look at compounded continuously first. Right, so this formula looks like this. A equals P e to the power of RT. Okay, most people call it the PERT formula. This formula was originally created to predict populations. They quickly found out that it was ineffective because one thing that this formula didn't take into account was the death rate or natural disasters. It was just taking in how much the population was growing. It wasn't looking at how it was also declining. Okay, so if we look at this, in this formula, P is our initial amount, and R is our interest rate, and T is the amount of years. Okay, so notice how I didn't tell you what E was. Okay, remember E is the exponential E. It's that number on your calculator that we use for natural logarithms. So when we do these problems, E is that number on the calculator. It's 2.17 blah 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 blah. It's just like pi. It's also a number. Okay. Alright, so let's look at an example of this. Okay, so this example says, Tamika invests $500 at a bank that offers 10% compounded continuously. Find the amount at the end of 5 years if untouched. Okay, the reason the if untouched part is up there is because if she puts more money in the account or she takes more money out, the interest will be different. Okay, so we're just assuming that it's untouched. So she just put the $500 in there and left it for 5 years. Okay, so using the formula that we just wrote down, PE to the power of RT. Okay, so we're going to identify what our P is, our initial amount, 500. Our R is our interest rate, 10%. which in decimal form is 0.10. And then our time was 5 years. Yeah. Alright, so now that we have identified everything, we can plug it in to our formula. Alright, so her money, her $500 grew to about $824.36. Alright, so the last formula that we need to look at is when the interest is compounded more than once. And this formula, so okay, so this formula, again, P is our initial amount. R is still our rate, our interest rate. And T is our years. Okay, N. N is how many times? So the number of times compounded. Okay, so let's talk about N real quick. So there's going to be different words in these problems that will tell you what your N is going to be. So you could see words like compounded quarterly, right? Quarterly, so 4 times. So my N would be 4. You could see semi-annually, right? That would mean that it happens 2 times a year. So my N would be 2. Easy one, monthly. So if it happens every month, that means it happens 12 times a year. Bi-monthly. Okay, that means it happens every other month. So that would be 6 times, right? Some other ones, daily would be 365, weekly 52, so on and so forth. Okay, so just be mindful of these words in the problems so you know what your N is. Alright, so let's look at an example. Okay, Jacob invests $500 at a bank offering 10% compounded quarterly. Find the amount at the end of 5 years. And again, we're assuming this is untouched. Okay, so our initial amount is 500. Our rate was 10% or 0.10. Okay, our N. Our word here was quarterly. Okay, quarterly means 4, so my N is 4. And then my T, my time, was 5 years. So plugging everything in. Okay, so my amount, or Jacob's amount, after 5 years, the $500 grew to $819.31. So if we look at the difference between the example with Tamika and the example with Jacob, they both invested the same amount, $500, and they both invested it at a bank that offered 10%. However, Tamika's bank offered continuous compounding, and she got a lot more money. Well, not a lot more, but she got more money than Jacob did. Alright, well, that is all I have. So you will need to remember those 3 formulas.